Hi and welcome to the videos for section 8.1. There will be two videos for this section and we kind of switch gears now. In chapter 8 we're going to start talking about the polar coordinate system. Section 8.1 will actually have some definitions, sort of talk about the conversions. So section 8.1 is polar coordinates. Now, unless you've had a trigonometry class before, you're most likely just used to, excuse me, the rectangular coordinate system. So the x-axis, the y-axis, that's known as a rectangular coordinate system. Polar coordinates, we're going to be dealing with circles. So that's what we've been dealing with pretty much all semester, the unit circle, degree measurements. That's what the polar coordinate system does. So here's our definition for polar coordinate system. We have that the polar coordinate system uses distances and directions to specify the location of a point in a plane. We choose a fixed point call this O for origin, and draw a ray which is like a half line called a polar axis. So each point P can be assigned a polar coordinate we identify that as P and then R theta. So R is the distance of that radius, theta is the angle from our polar axis. So again, where where R is the distance from O to P, and theta is the angle between our line segment OP and the polar axis. So what this looks like in pictorial format is we have our point O, we have our ray, which is our polar axis. It's kind of like half of the x-axis if you want to think of it that way. Then we have some point out here, P. The angle from the polar axis to P is our theta, and the distance of this line, or the length of that line, is r. So then we have a few things. For theta, it's positive if we're going counterclockwise, just like when we were dealing with the unit circle. It's negative if we're going clockwise. And then our R can be positive or negative. If negative, then it's the point that lies the absolute value of our units opposite of theta. So what this means is if I'm given, so this point here would have values P is equal to R times, R and theta. Distance of R, angle of theta. If I was given the point, if I was told to plot where is P minus R theta, well, the first thing I'm going to do is move the direction of theta, which puts me in line with this blue line. But because it's minus R, I don't go out this way, I go back the other way. And the length of this is whatever the value R is, take the absolute value, because length isn't a negative length. So this is my point minus R theta. And this causes a lot of trouble with people, I'll tell you right away. So if you have questions about this, make sure you ask in class next time we talk about this. If we have a negative, we're always going to move in the direction of our theta to begin with. We move in the direction of theta, and then if R is positive, we just move out from that point. If R is negative, we move opposite of what that angle is, the absolute value of R. So hopefully that is clear enough. Like I said, if not, please ask during the class when we discuss this topic. Okay, so let's look at a few examples. So let's say we want to plot the point. The first one we're going to do is 1 3 pi over 4. So I have my origin, I have my polar axis. So the first thing we're going to do is move in the direction of theta. Theta is 3 pi over 4, which puts me where? Puts me over in what I used to think of as quadrant 2. So it's that line there, kind of running upper left to lower right. That's theta is 3 pi over 4. My radius is 1, which is positive, so I'm just going to move out 1 unit here. So this would be the picture that I get. So this is the graph, this solid blue line of the point P 1 3 pi over 4. What if I have the point 3 and negative pi over 6? Well, again, I'm going to start with my polar axis, move in the direction of theta. So that's minus pi over 6. So because it's negative, I'm moving which way? This way, right? So that line would be that dotted line. And then my distance is positive 3, which means I'm just, whatever direction this line was going, in the direction I moved, I'm going to move out 3 units in that direction. So it gives me that picture there. That sort of double blue line that I drew. So that's my point 3 minus pi over 6. And then lastly, what if we have the point P negative 4 pi over 4? So again, I'm going to draw my polar axis. Pi over 4 is what? It's this 45-degree line But because we have r as -4, I'm not going to move out in the direction of pi over 4. I have to move the opposite direction. And then it's -4, the absolute value, which is 4 units down this direction. So that's the 3 different possible cases. Both are positive. When theta is negative, it means we're just going clockwise with our theta. But then this is the tricky one for people. So we move theta to start with, pi over 4. But because it's negative, I'm not moving out this way, I'm moving the opposite direction. So that gives me that picture there. So we can also write these angles as follows. So if we have some point, so here's my polar axis, here's this point P, r theta. Well, looking at this last picture, what can I say? This is the same as if from this point I moved how far? A direction of pi. But if I'm down here to get to this point, what do I have to do? I have to do the reflection, the minus r. So P, written as r theta, can also be written as P minus r, and then theta plus pi. So we can represent this point in a couple different ways. I can just have it as P r of theta. I could have it as minus r, but I have to add pi to the degrees. You can also write it as r of theta, r in theta is equal to P r theta plus 2n times pi. So this is sort of like when we were finding all the solutions in section 7.5. Same idea. This point here is r, but if I go 2 pi times 1 times 2 times minus 1, it still gets me back to that same point. So again, these polar coordinates we can represent with this 2 pi notation, or pi, if we're talking about like the negative r. We can also have that P negative r theta plus pi is the same as P is negative r, and then theta plus pi plus 2n times pi. Kind of a big mess. Again, I would worry, or I would focus more so on these first two. But the third one is another way in which we can represent this. So let's look at an example. Kind of problem you might get here. I'll be honest with you, you're not going to get one on exam 2 or exam 3 of this following type of question. But it's just checking concept. Do you understand how we can represent these points within a polar coordinate system? So you still need to know how to do it, even if it's not going to be on the exam, because you're going to have to be able to find these points within a polar coordinate system, and you may need to use these techniques to do it. So the problem is as follows. We want to graph the point P 2 pi over 3 and find two others with r is greater than 0 and two others with r is less than 0. So first, let's graph this thing, see where this thing ends up, what our picture is supposed to look like. We're going to start with our theta, pi over 3. That takes us to here. And then we're 2 units away, our r is positive. So it basically gives us that right there. So now, if we want 2 more with r is greater than 0, what do we do? Well, we're just going to add 2n pi to each value of theta so that we get a full time around the circle. So first thing we can do is p. Our value of r stays the same. Our r is positive. And it's just pi over 3 plus 2 pi. And pi over 3 plus 4 pi. So the first one is if we go a full time around the circle. Second one is 2 times around the circle. But we still end up at that point. If we simplify this, we just get p is 2 and 7 pi over 3. Or p is 2 and 13 pi over 3. These two coordinates have the exact same as this one here. Now the one that gets a little tricky. R is less than negative. So that means we're going to have negative 2 something, negative 2 something. So that's this sort of first equation here. So what we need to do is take our theta and add pi to it. So pi over 3 plus pi. So when we do that, we get p is negative 2, and then if we add these two together, pi over 3 plus pi gives us 4 pi over 3. We're just adding 3 over 3, so we get 4 pi over 3. So now from this one, we want to basically add another 2 pi. So what this picture, this number 3, if we call it 3, it's the point negative 2, 4 pi over 3. So we would move a distance of 4 pi over 3, which puts us down here, but because of the negative value, it jumps us back up to that point. So it's still the same location. So now from here, we would just want to add another 2 pi. So we're basically doing this guy here, negative 2, 4 pi over 3 plus 2 pi, which then gives us the point negative 2 and 10 pi over 3. So that's our solution to this. The graph, 2 with a positive r, 2 with a negative r. All 4 of these, actually all 5, the original plus these 4 that we generated, are all dimensions for this same point. And you can see how the rectangular coordinate system, the polar coordinate system differs from the rectangular coordinate system. In the rectangular coordinate system, what we just have an x value and a y value, puts us to here. We can't use positive and negatives to move that point around. But with the polar system, we can add values to the theta, we can change the r to positive or negative, and it'll still get us to that same location. So there's sort of the introduction to the polar coordinate system. Come on back, we'll show you how to convert from polar to rectangular and so forth.